Tiger team, this room is yours.
On the southern tip of Africa, an engineer sat in an office noodling on a problem. Not a stark, brightly lit office filled with cubicles and boring furniture, nor yet a gloomy, musty office that smelled of damp walls and busy humans. It was an office in Cape Town, and that means bright, natural light, colorful people, and a sense of opportunity. That engineer was me, and I'd worked in the payments industry for almost a decade. The last few exposed to fast-growing world of cryptocurrencies, working on an open payments protocol called Interledger. And I must say, in all that time, I'd seen a lot of ledgers. And any system that processes payments needs to record these in ledgers and track balances of the impacted accounts. And in most cases, these are implemented as a combination of some sort of generic database or key value store where you store your, you persist the accounts and you keep your shared state. But those are combined with application code where you implement the business logic and, most importantly, the accounting logic and accounting policy. And in most cases, the implementations of these ledgers left a lot of room for improvement. And the reality of payments is that they're a challenging problem domain. It's unique in nuanced ways. In the first instance, financial systems need to be 100% accurate, auditable, can never lose data, which by itself is not unique to payments, but it's a constraint that adds a lot of complexity and cost, especially since payment systems operate as distributed networks, meaning regular reconciliation, dispute resolution, and so on. And those processes add a lot of cost to the system. So with our team and Coil, our company's involvement in the Modulu project over the last 6 years, we've learned that eliminating the need for conciliation and disputes leads to low cost for the whole system. And that further leads to a more accessible and more inclusive payment system overall. The second challenge with payments, probably the biggest one, is the need to track balances. So when you're processing payments, you need to update balances in real time. And that's really hard to do at scale. Throughput is limited per account. And so updates to the balance have to be done in order, and accounts become your unit of sharding. So transactions that impact the same account just can't be processed in parallel. And so many of the common horizontal scaling and sharding techniques are just impossible when you're doing payments processing. And so no matter how many instances of your processing logic you run, the balance on an account is shared state that has to be locked, updated, released for each transaction in sequence. And so it's very hard to scale a ledger without cutting some corners, sacrificing performance or safety or both. The challenge of scaling is even more accentuated or emphasized when you're dealing with hubs. So payment hubs that are switching payments or acting as payment clearing systems feel this acutely. And we felt it when we were developing the Interledger protocol at Ripple and further developing it within Coil, because Interledger is intended to serve really high volumes of low value payments. That was our goal. And the reason that this challenge of dealing with account-based sharding is emphasized is because hubs or payment switches generally have a very high ratio of transaction throughput to the number of accounts. They hold accounts for peers, not for end users. And so they generally don't have many accounts, but they're processing a lot of volume because they're switching transactions for a lot of peer systems. So obviously, high volume of transactions per unit of sharding means very hard to scale. So I suppose the obvious question is, who needs that problem solved, and why hasn't it been solved already? And why was I sitting in this office in Cape Town noodling on this problem in particular? And the reality for me is that one of global payments industry's biggest flaws is also actually its saving grace. The vast majority of payments are never switched out over global networks. Payments are very siloed. They're stuck in jurisdictions, and they're limited to currencies. And that's one of the reasons why I think cryptocurrencies have become so popular, is because they create this global payment network that's accessible and easily and accessible to anyone and easy to use. And that's how we felt when I was at Ripple, that the future is global, that payments networks need to have global reach. And when I worked, at Ripple and now at Coil, we've always believed in this idea of the Internet of Value and the power of the web as a worldwide platform. So when you bring those two together, how do you enable payments on the web that are global? And so, we've always thought of this idea that payments should be able to move as quickly and as easily globally as information does on the internet. And that should allow anybody around the world, as long as you have an internet connection, to do business with anybody else, not just share information, but actually do business and commerce. So our work on the Interledger protocol is the first step towards that future. And then we participated in the Moduloop project, and that was a very specific application of Interledger, servicing the poor and people without access to traditional financial services. And combining that with all of my time prior working in the card industry, I'd always seen payments processed using sort of sticky tape and string solutions. Like I said, generic databases and key value stores banked together with application code. And generally, the payments processing itself then required complex back office processes that would take all of that payments data and reprocess it to actually account for it and turn it into financial accounts for reconciliation and reporting. And so my theory, as I was sitting noodling on this problem, was that it should be possible for us to actually record payments as accounting entries. And why couldn't we have a really high-speed accounting system from the start? What if we had a Xero or a QuickBooks or similar system that could handle 1 million journal entries per second? And then every payment gets recorded and accounted for in real time, rather than this sort of two-phase process that seemed to me to be holding everything back. Anyway, I had been discussing this internally with the team in Cape Town, and we had talked about Postgres SQL extensions inspired by the work on Timescale DB, and we'd never really gone beyond theories and ideas. And fortunately, as luck would have it, our opportunity to build a high-speed accounting database came along sooner than we'd expected. One of my colleagues, Don, was working on a performance workstream in the Moduloop project. And, I'd met Joran, and Joran joined us because of his, node expertise. And we were really trying to squeeze out some extra performance out of Moduloop stack. And well, I'm kind of getting ahead of myself. So let me leave the story to Don. But first, let me start by introducing you to Don. He's the Tiger team's very own rocket scientist. And he's the only one of us to hold a Guinness Book of Record. In this case, for the highest launched air compressed rocket. So Don was the guy that saw the opportunity for us to bring this idea we had noodled on into reality by solving the performance problems at Moduloop specifically. And he can explain how the story unfolded from there.
Cool. Thanks, Eddie. So speaking of rockets, Adrian is like our resident Gandalf. He's been around, he saw the problem, and he put the team together and sent us off on our journey. And he's always there with sage advice, a wizard's sense of humor, and a few fireworks of his own. So this rocket project was great fun because it taught me that sometimes the simplest solutions are the best and end up being the most elegant. For example, the final design to release the parachute relied on a 15-year-old spring we found in one of those old toilet paper holders. But of course, the most exciting part was actually just launching something high into the air. Anyway, so this lesson served me well when Joran and I were doing the performance work on Moduloop. So in that work last year, we went about tracing all the SQL queries that got executed when a payment is made. And we found that the number was about 20 queries per transaction between two parties. And many of these queries were writes, so the costs of fsyncs were multiplied along with all the associated network hops. So we set about interviewing people and did a survey of the research to see if we could find a better solution. And the best we found was to use stored procedures to do one database query. But this left little room for business logic and provided only one order of magnitude improvement. So we then asked the moonshot question: how could we make the system 100 times faster and 10 times cheaper to run? And the breakthrough for us was realizing that everything is a batch. Whether it's a batch of 1 or a batch of 10,000, everything is still a batch. So this batching is a powerful idea because if your interface has first-class support for batching on both request and response parts, you can then amortize things. You can amortize your F-syncs, you can amortize your network hops, you can even amortize loading your functions instructions code into the CPU's instruction cache if you have a whole lot of the same kind of data you want to run through the same function. So we then decided to test this theory with a minimum viable product, and thus TigerBeetle was born, which we wrote in JavaScript. The MVP proved to be a success, and TigerBeetle had a throughput of about 200,000 financial transactions per second. So now, with the prototype in hand, we needed to decide what language we would write TigerBeetle in. Would it be C, or maybe even C++? Joran, who had done the modular performance work with me, had at that stage been improving his performance on the football field. And luckily for Messi, our resident Gandalf convinced him to turn his attention to improving payments infrastructure instead.
As Don said, I literally bumped into Adrian on the soccer field. Chatting with Adrian after the game, I heard about his experience with Ripple, Coil, and Interledger. And the next thing, Don and I were doing performance analysis on Mojaloop, which was a fantastic opportunity. Working with Don was a great learning experience for me, how to think about methodology up front. Around the same time, I was writing mostly in C for a storage system and also for a static analysis security tool to help Microsoft protect their software release pipeline from 0 days. So for writing TigerBeetle, I felt most comfortable with C. There were aspects of C that needed to be fixed, but without losing the simplicity and power and orthogonality of the language. As a lucky break, Zig was well on the horizon. I think the way to catch a wave is not when you see the surfers already on it, but when you see the swell. This photo is what I think of when I think of Zig. It captures the simplicity, the precision, the style, and the quality. I first saw the Zig swell in 2018 and got excited. I was late to the party and started sponsoring the language in 2019. And then in 2020, Zig looked like an awesome break, the perfect swell. TigerBeetle was going to be written in something simple and powerful like C, and here it was, but with orders of magnitude more safety and remarkable readability. And we started paddling for it and saw that some talented developers had the same idea. And that's how we met Isaac. Isaac's Zig Showtime talk on River last year was fantastic and a huge part of the reason we started writing Zig. Isaac was always there on IRC with a lot of positive energy, helping us out with questions, even talking about TigerBeetle at the same time as we were thinking he could help accelerate the pace.
Like Joran, I've been searching for a language to replace C for my use cases since quite some time. I tried many, but none stuck until I decided to try out Zig for the Wayland compositor, now known as River, that I started working on early in our global pandemic. As it turns out, I really liked Zig, and my first Zig project ever has grown into a tool that I and a growing number of others use daily. Since then, I've also gotten involved with the development of the Zig compiler itself, contributing various features to support River's development, as well as to push the self-hosted compiler written in Zig forward. I was offered the chance to join the Tiger team several months ago. I've been working on TigerBeetle since this past March. But where would we be heading, and how would we chart a course?
With the journey begun and the formation of a fellowship, it would befall upon us to chart a course. From the SQL Shire through linear programming, Mirkwood and Maya, towards the distributed dragon and consensus fire of the lonely mountain spire, where waits the bounty gold and protocol of legend untold.
Entomologists who have studied tiger beetles have long found that one of the 10 habits of highly effective tiger beetles is that they begin with the end in mind. If we were to chart a course, what should the destination be? We came up with 3 goals. Safety. How can we make the system safe? Performance. How can we get 100 times more performance with 10 times weaker hardware? Features and experience. How can we make the system easy to use and simple to maintain? The most important of these goals is safety, so let's start there.
Just like in security, where you might start with a threat model, in other words, all the ways you think an attacker might try to attack your castle so you can defend against them, for safety we started the same way, with a fault model. And in particular, the storage fault model, because TigerBeetle can't afford to lose people's money. The network fault model is well understood. However, the storage fault model is less well known and has also seen some earth-shattering research in the last year or two that has shaken the foundations for distributed databases and what they need to contend with. So much so that they must almost reconsider major parts of their design. For example, in 2018, there was what was called F-Sync Gate. This was where Postgres would retry an F-Sync after an F-Sync error, and then discovered that F-Sync on Linux did not work the way they thought it did, with disastrous consequences. They realized that if a queued I/O or buffered write fails to F-Sync and make it to disk, then the kernel marks the dirty page as clean in the kernel page cache, even though the data never made it to disk, so that subsequent F-Syncs report a success. Postgres responded to F-Sync Gate by panicking after an F-Sync error, and many other applications like WiredTiger, MongoDB, and MySQL followed suit in fixing their F-Sync retry logic. However, in 2020, the University of Wisconsin-Madison tested Postgres, along with LMDB, LevelDB, Redis, even SQLite, and found that all of them still did not recover correctly from F-Sync failure. For example, Postgres would panic, but after a panic, it would come back up again, read the write-ahead log straight from the kernel's broken page cache, and base subsequent decisions on data that was never durably written. In another landmark paper that won Best Paper at FAST 2018, called Protocol-Aware Recovery for Consensus-Based Storage, UW-Madison showed that distributed databases do not correctly distinguish between corruption in data written several days ago from corruption in data written just before a system crash. Because they conflate what is called bit rot with a system crash, if they find a corrupt sector anywhere in the middle of the committed log, they delete the rest of the committed log, all the rest of the committed data, just as if it was the last thing written before a system crash. In other words, transactions that committed long ago and that were acknowledged even to the outside world are now suddenly deleted much later without any explanation by the database, leading to data loss. Worse, however, was when they showed that this mistake in local corruption recovery can not only cause a single cluster server to lose data, but can also actually propagate through the global consensus protocol and cause an entire log cabin or Kafka cluster to lose data. The best part of the paper for me was how they showed exactly how to improve the design of a distributed database so that the local storage and global consensus protocol all work together in how they do fault-tolerant recovery. With this technique from UW-Madison, TigerBeetle can maximize disk redundancy to guarantee that committed entries will never be lost, as long as one copy of an entry remains, and that the cluster is unavailable only when all copies are faulty, but not before. ZFS is a hero in this space, and this talk by Jeff Bonwick and Bill Moore called ZFS, the Last Word in File Systems, is well titled and well worth watching. Thanks to UW-Madison, we saw that for a distributed database, your local corruption recovery strategy needs to interact with the rest of the cluster for safety and for availability, which is why, apart from the licensing issue, we couldn't, unfortunately, just run ZFS under TigerBeetle. But we did appreciate how ZFS actively set out to handle misdirected reads and writes. This is where the software or hardware dereferences the wrong disk sector and reads from the wrong place on disk, or overwrites data it was not supposed to overwrite. This influenced the design of ZFS, and ZFS solved the problem by daisy chaining or hash chaining checksums all the way back to the file system superblock. Because all the checksums overlap each other, you can immediately see when data gets reordered. This was such an elegant solution to misdirected I/O, and I think that if you can have this in your fault model up front, it becomes much easier to handle. We've seen an interesting mix of storage faults, broken kernel page cache, local corruption that leads to global cluster data loss, and writes that go to the wrong disk sector. To cap it off, there are also what is called gray failure latency spikes. A gray failure latency spike is just where the network or disk suddenly slows down dramatically with multi-second latency spikes. What took a few milliseconds now takes tens of seconds. It's a thorny problem when things don't fail completely but limp along. You can imagine the effect this can have on your cluster. In fact, in a study by Microsoft Research, the big availability breakdowns and performance anomalies in cloud environments that they analyzed were caused by gray failure rather than fail-stop failure. At the same time, slowly failing components can also return eventually to normal performance levels and often do. For example, a solid-state drive undergoing garbage collection might become many times slower than the other drives in the cluster, but then return to median performance. The challenge with gray failure latency spikes then is that on the one hand, these temporary slowdowns can cascade into major availability breakdowns, but on the other hand, because they're temporary, it's also not cost effective just to replace the hardware. So from the outset, it was important for TigerBeetle to not only have storage fault tolerance, but also have tail latency tolerance, because the upside in solving this is more predictable performance and a smooth experience for the operator.
I suppose no storage fault model would be complete without noting that file system developers are well aware of the issue. We can see this in some of the best file system comments. For example, from the source of XFS, just ignore errors at this point. Also from ext3, error, skip block and hope for the best. Instead of hoping for the best, we want TigerBeetle to handle all these storage faults and also keep on running with predictable performance.
It's time for a quick multiple choice question. Everybody loves a quiz. We wanted to ask the question now to give everyone time to answer. If you're on Twitter, we've started a live poll. You can find it under the TigerBeetle DB handle. The hour grows late, and the shadow of Mordor approaches Gondor. Don's just flicked our power switch for us. The shadow is getting close. If you're on Twitter, we've started a live poll under the TigerBeetle DB handle. So you'll see the poll there, Twitter, TigerBeetle DB. Pop over there, quickly see what you think. You can also drop your answer in the Twitch chat a little later when we come back to it. And the question is, which of the following is the monotonic clock for elapsed time? For example, for a distributed database to measure elapsed time for something we would never recommend, something dangerous like a leader lease, which of the following is the monotonic clock? Is it A, clock monotonic raw? Is it B, clock monotonic? Is it C, clock boot time? Or is it D, none of the above? We'll come back to this in a few minutes after we look at TigerBeetle's network fault model. While the network fault model is much more well known than the storage fault model, it's still tricky.
Because packets may be delayed, packets can also be reordered. And just like our storage fault model, packets can be corrupted and misdirected. Packets can be routed to the wrong address as the network topology changes. We can't assume that a server will always have the same IP address. We might send a message to a server and find we're actually speaking to a completely different cluster. And of course, packets may be lost.
Which brings us to an interesting question. If some network packets can be lost, while others make it through, what happens to network time protocol and clock synchronization during a network partition? Well, NTP stops working during a network partition. With no network time protocol to synchronize clocks, servers could soon start to run wild and get disconnected from true time, with significant drift even during a short network outage. But within a matter of hours, you could find your cluster playing all three Back to the Future movies simultaneously. And unfortunately, it turns out that this is really common in the real world too. It's not a problem if network time protocol and your cluster are all partitioned in exactly the same way, and if you can be sure that they both stopped working at exactly the same time. But what if network time protocol and your TigerBeetle cluster don't fail together at exactly the same time? What if you're a bank and you have strict legal requirements for the accuracy of your transaction timestamps? And what if network time protocol stops working, but your TigerBeetle cluster keeps running? And then the TigerBeetle leader jumps a few years ahead. It's a good idea to have a clock fault model at this point. TigerBeetle's clock fault model means that we need a way to detect when there are too many clock faults in our cluster. In other words, when network time protocol has stopped synchronizing the cluster's clocks. TigerBeetle does this with a really elegant algorithm called Marzullo's algorithm, which can estimate lower and upper bounds on accurate cluster time from a number of noisy clock sources. Whenever a TigerBeetle server sends keep alive probes to another TigerBeetle server, it also takes the opportunity to measure the clock offset to the other TigerBeetle server. Then it checks how wide the bound on cluster time is and can clamp the leader's system time if necessary to not exceed the cluster time. This prevents a leader with a clock in the far future from pushing all subsequent timestamps out into the future. For example, here are TigerBeetle's log messages when it sees that 1 out of 3 replicas has a faulty clock. It can see the confidence interval on the clock error, and the faulty clock can then clamp itself to cluster time, so that hopefully a TigerBeetle is never late, nor is it early, but timestamps precisely when it means to. Which brings us to our riddle. Which of the following is the monotonic clock for elapsed time? For a distributed database to measure elapsed time, we believe that the best monotonic clock source on Linux is not a clock monotonic raw. And the reason is because that was only exposed by the kernel, we think, for synchronization protocols like NTP to measure the quartz crystal drift error. And so it can have very little resemblance to the actual passing time. The answer is also not D, none of the above. And surprisingly, also not B, clock monotonic, but rather C, clock boot time. What are the two hardest things? Cache invalidation and naming things? Well, we were looking for a monotonic clock, and the name clock monotonic jumped out at us. It sounded just right, like what we needed. But then we read the kernel man page, always a good thing to do, and we saw that clock monotonic stops measuring elapsed time while the system is suspended. For example, I think during a VM migration, which can happen in the cloud. And this would be catastrophic if a database used clock monotonic to measure time for something dangerous like a leader lease, which again, we would never recommend that any one of us try at home. But clock boot time is exactly the same as clock monotonic. The great thing about it is it just also measures elapsed time even while the system is suspended. So this shows how easy it is to make mistakes in our assumptions, which brings us
a
to
human fault model. Sufficiently complex software is nearly impossible to get correct on the first try. Programmers will write bugs on occasion, no matter how talented they are. In order to detect these inevitable bugs in our code, our primary tool is assertions. An assertion tells the compiler that some condition is guaranteed to be true, barring any programming error on our part. In Zig's debug and release safe build modes, assertions are safety checked and guaranteed to cause a runtime panic on failure. To make our lives easier, the Zig compiler inserts many of its own assertions in safe build modes as well, checking for things such as out-of-bounds array and slice access, integer overflow, etc. Although the goal is to write perfect software which has zero bugs and never triggers assertions, assertions can often turn what would otherwise be a critical correctness bug leading to data loss into a mere liveness bug. When properly used, assertions encode assumptions that the surrounding code is written under, acting as additional documentation that is safety checked at runtime. For example, from our code, this onAccept function has several assumptions that must be true when it is called, otherwise the code will not work as intended. And since these assumptions are subject to changing due to refactoring, this is a way to make our code base much more robust to introducing bugs due to refactoring. As useful as they are, it is critical to note that assertions are not a replacement for error handling. In contrast to bugs in our code, errors may arise which are not our fault. For example, sending data over the internet may fail, writing to a file may fail, the user may provide invalid input. Robust code must account for such errors and handle them somehow, without invoking undefined behavior in non-safety check build modes. This could mean retrying the failed operation, or, for example, simply panicking. This can be a totally valid way to handle errors in some cases. In fact, TigerBeetle itself will panic, relying on replication and the consensus protocol to recover from select errors, such as if the kernel's monotonic clock ever ticks backwards, or if we encounter an error while writing to disk.
And finally, this is a fun one. Packets may be replayed many hours later. The system has moved on, and our blast from the past arrives to set everything back. And after safety, our next goal is performance. How can we get 100 times more performance with 10 times less hardware?
And how can we get more performance without compromising safety? The concepts of control plane and data plane are often used in networking. You can think of the data plane like a water mains pipeline with huge volumes of data flowing through and nothing inside to obstruct the flow. The control plane, on the other hand, would be all the safety checks you do outside the pipeline as an operator, the little control box that adjusts pressure and decides where the water should flow. In TigerBeetle, we think of the data plane as the work that scales 1-for-1 with the number of financial transactions per second, whereas the control plane is work that is several orders of magnitude less in terms of CPU, memory, network, or storage, but more likely to have catastrophic consequences if gotten wrong. The distinction between the two planes is useful because it allows us to exploit the inverse profiles, where the data plane is optimized for speed of processing and where the control plane is engineered for the safety of that processing. In the control plane, we want plenty of assertions with double and triple checks for safety, whereas in the data plane, we want to optimize for cache misses, context switches, and branch mispredictions. How does this work in TigerBeetle? Well, as a concrete example, we have around 10,000 financial transactions in a batch. A single threaded control plane is responsible for switching each of these batches through the cluster, and we amortize all runtimes bounds checks, assertions, and I/O across the batch, so that these become almost free. Yet we have literally hundreds of assertions in the control plane. In fact, we have about as many as the entire Zig standard library at this time, and we're doing an fsync on every single write. Having this clean split between control plane and data plane in the design provides both safety and performance without compromising either. All this helps to keep it simple, keep it fast. There are always compromises. In the case of TigerBeetle, our domain is tightly scoped and very simple, and we want to exploit the simplicity for performance. Batching is the biggest one by far, but here are some more Tiger tricks we've learned along the way. First, we allocate all memory and disk storage TigerBeetle will ever need in advance on startup. This means that TigerBeetle performs 0 allocations at runtime, which reduces overhead in the critical path and avoids handling out-of-memory errors at runtime entirely. We really appreciate Zig's philosophy of no hidden allocations. Next, we make a trade-off and limit ourselves to little endian architectures so that we can avoid byte swapping in our network and storage protocols. Since we also use fixed-size data structures for everything, this means we can simply reinterpret the bytes received over the network as a struct without any copy or other deserialization overhead. These fixed-size data structs are all aligned up to a 64-byte cache line to avoid straddling cache lines and to avoid false sharing, and are 1 or 2 cache lines at most to conserve per-core memory bandwidth.
Without blocking I/O or locks to block the CPU and slow things down, a big bottleneck for TigerBeetle is the CPU being blocked on blocking memory I/O. One way to think of memory is just as a slightly faster disk. It's probably a good way to think of memory like that, because compared to the CPU, main memory is really slow. So we try to avoid cache misses as much as possible. One way to do that is to avoid mem copies. We don't always think of a mem copy like this, but as far as I understand, to some degree, it uses up and flushes your L1 through L3 cache. So reducing or amortizing mem copies in the data plane not only saves CPU cycles, but also speeds up subsequent loads by not thrashing the CPU cache in front of main memory. In the same spirit, another big win for reducing cache misses is something as surprising as direct I/O. That's because we no longer need to spend CPU cycles or CPU cache on doing mem copies again to the kernel's page cache, which we also want to avoid for safety. We get a roughly 7% throughput win just from direct I/O. With some storage devices like NVMe devices so incredibly fast these days, doing a synchronous syscall into the kernel is actually now on the same order of magnitude as the latency of an I/O operation, 1 or 2 microseconds, which is the cost of the context switch into the kernel to make the syscall and the cost of the context switch back out to user space to return the result. It's the there and back again cost. There's a real opportunity cost to syscalls. What if there was a way to submit I/O into the kernel, but without syscalls? What if instead of doing a syscall, we could help ourselves to another I/O instead? We also try to avoid the complexity, rest conditions, locks, and context switches of multi-threading. We just think multi-threading is too hard for us. Instead, we use the kernel thread pool as the data plane. But how is this even possible? Thanks to IOU ring, you can now use the same interface for all I/O, networking and disk. This makes your program so much simpler. You get a unified I/O interface, and you also get to use the kernel thread pool as your data plane, just by dropping commands into a ring buffer and amortizing syscalls with a single IOU ring enter syscall. This amortizes context switches away right down to 0 and has some real performance benefits, especially if you sometimes do sector-sized I/O, like TigerBeetle has to do when it checkpoints the log. Some of our very rough benchmarking that we've done has shown almost a doubling of throughput for these 4 kilobyte sector writes, which is pretty amazing. Along with these goals of safety and performance, there was one more question left to answer before we could embark on the design of TigerBeetle. We had to ask ourselves, what should the features be? How could we make the system easy to use and simple to maintain for operators? In the past, as Adrian said, developers building financial apps had to glue everything together with multiple queries, moving the data back and forth across the network to run business logic. We realized that all this generic SQL work was simply to recreate double entry accounting. This was the second breakthrough for us at a feature level and defined a set of features that TigerBeetle as a database would expose. Everything is double entry accounting. Everything in financial transactions comes down to debits and credits and accounting policy. We asked ourselves, what if we could just make these accounting primitives first-class features of the database? What if we could invert that equation and move the code to the data to enforce the accounting policy needed to transfer thousands of amounts between accounts, but all in a single database query? What if TigerBeetle could do double entry accounting like Newton's third law? For every credit to an account, there is an equal and opposite debit from a different account. No tables, no rows. As that really classic post on Hacker News today said, no more SQL, just accounts and transfers between accounts. This would let developers model their financial domain as it is, a chart of accounts. Instead of designing complicated SQL schemas across tables, developers can design a real chart of accounts for the perfect schema to match their domain. With our goals and features in mind, how would we implement the database? What would the actual design look like? For this, we would do nothing revolutionary except stand on the shoulders of giants. Martin Thompson is one of those giants. He was one of the co-founders of Almax. They designed one of the first high-performance trading platforms to do more than 1 million transactions per second using lock-free ring buffers to avoid contention. He coined the term mechanical sympathy, and I've learned a huge amount from reading his blog over the years. It just so happened that in July last year, as we were designing TigerBeetle, Martin did a fantastic talk on the state of the art in financial exchange architecture. He's worked on many of these low latency systems in Java and C over the years, and what follows is more or less the design he described. First, we start with what in computer science is called a replicated state machine. It's actually just a simple recipe for implementing a fault-tolerant service by replicating servers and coordinating client interactions between these server replicas. Like C-types or C-pointed declarations, I find that if you just read it backwards, it makes more sense. So you have a machine, i.e. hardware that fails. It's got some state on it, like a hash map, and you then replicate this for fault tolerance. Replicated state machine. What does this look like in practice? So you can make an RSM in 3 easy pieces. First, you append the command to disk, and you can imagine this is exactly like Redis, how it writes commands to its append-only file. Next, you replicate the command to another disk, hopefully on another system. And finally, you apply the command to your state, for example, by updating your hash table. The only thing you need to make sure is that you do these 3 steps in the same order everywhere so that each machine arrives in the same state. Then if a machine crashes, you can catch up and replay the log to get to the same state. This will give you the highest level of consistency, what Carl Kingsbury of Jepson would call strict serializability. This is really the gold standard of consistency, and there's nothing higher. Within a machine, in TigerBeetle, we keep the log order the same by daisy chaining or hash chaining our log entries, just like ZFS, so that we can detect and recover if the kernel or firmware reorders the log by writing to the wrong place on disk. Across machines in practice, if you have a cluster of 3 machines, and if you can make one of them the leader, then you can have this leader order the way in which commands are appended to the log. But what do we do if the leader fails? When the leader fails, we can elect a new leader using what is called a distributed consensus protocol. And that's just something that lets you guarantee that the majority of the cluster have consensus on who the next leader should be. We found that the simplest way to do this is with the view-stamped replication consensus protocol invented by Brian Oakey with Barbara Liskov and later revised by James Carling. View-stamped replication pioneered the field of consensus in 1988, a year before Paxos, and provides the same consensus guarantee as Paxos or Raft, except with a huge advantage that you also know who the next leader is going to be. There's no confusing randomized voting process. Instead, it's just a simple modulo function of what is called view number. Each server starts with a view number of 0. When it doesn't hear from the current leader, it bumps its own view number, and all the other servers do the same. If a majority of servers now share the same view number, then the next leader starts operating. We found you can also squeeze this deterministic leader election idea for some really cool performance optimizations, which we will be documenting in our repo in the next few days. The 2012 revision of the protocol is the perfect place to start if you want to take something like Redis and make it fault tolerant. And to help you do that, we're also making TigerBeetle's view stamp replication implementation completely generic over the state machine in the next few weeks. So you can plug and play and be up and running with your own state machine, but with all the fault tolerance that TigerBeetle's implementation of view stamp replication already provides. Every language gets a consensus protocol written for it eventually, but we're hoping that Zig's approach to safety, precision, and remarkable readability are going to make Zig a truly outstanding language for writing distributors without factoring Zig's superpower, its unique ability to comp time.
The way we've structured our code separates the view-stamped replication protocol implementation itself from the lower-level code integrating with the host system and even from the state machine itself. This lower-level code includes abstractions over the system clocks needed, the storage for our log, either on disk using the file system, in RAM, or whatever else you would like to use, and the message passing abstraction for networking based on our message bus. And this message bus merely allows sending messages to a target server or client, which can be implemented over TCP, UDP, even Quick, or whatever else you could think of, maybe Unix domain sockets. We want to do everything locally. And so the state machine is the only part of our code that implements the business logic related to accounting data, which means that you could swap out the state machine, as Jordan mentioned earlier, for anything else you want. And the rest of TigerBeetle's code could theoretically be reused with 0 modifications to implement whatever kind of business logic you want for any kind of replicated state machine. And so this is kind of our high-level architecture of our code base right now. And as a bonus, this clean separation of components allows us to do really nice deterministic fuzz testing and automated fault injection. For example, by swapping out the storage implementation with a faulty storage implementation that returns intentionally faulty data on occasion to then test our protocol's ability to recover. And this is what we're working on currently. This is currently not what we have implemented right now, but this is our end goal that we're moving towards. And so the journey to distributed consensus continues as we move TigerBeetle from alpha to beta. I hope to see you all in Zigtember for a special interview and a round table to go deeper into view stamp replication with pioneers of the protocol themselves, and a $20,000 challenge to see view stamp replication made famous.
Everyone, is this it, or is there more?
Yep, that's right.
That's right. Okay, I wasn't sure because now you made me.
The stream is yours.
Yeah, you made me paranoid. Now I was wondering, am I losing packets?
That's the right way to think about stuff.
Yeah. So this talk was incredible. Let me start by saying this. Thank you all so much for the effort that you put in. That was a lot of fun, for real. I think everybody enjoyed it. Also in chat. So I guess this is the moment for people to start asking questions. So you can write them in chat, and I'll relay them to our guests. While people come up with questions, I have the standard question, I guess. But since this is it's a group thing, and it's also it's a big business project, I have a slight different version than the usual question. Well, so usually ask people, how did you find out about Zig? In this case, what I want to find out is, Joran, I think you were the one who discovered Zig, right? And introduced Zig to the project. Okay, so can you Can you recount the experience of one day going to the office, having a meeting, I guess, or I don't know what the precise setting was, but like the first moment when you sit down to people around the table and you tell them, so I found this language, it's still super alpha, it's made by a guy in New York, he used to work for a dating website, and I think we should build our serious financial database using that language. Like, how did it work? How did you convince them?
Oh, wow.
You're muted. You're muted. Oh, okay. No, sorry. I
Lewis.
can hear you now. Okay. Sorry, you were saying?
I just said to everyone, well, I see therefore a Zig, and that was all cool. And no one ever asked us since then. We just all said, well, we're going to write this in C, and actually saying that, everyone said, no, use Zig. Got better compilation chain. They just said we don't want to worry with like C's build system. Bring Zig. And there was also a lot of drip irrigation going on. So thanks to Showtime, we would be sharing Showtime talks. Andrew's talk on Zig's awesome async that we shared. We shared like internally about Zig's error handling, how you can, the Zig compiler can actually tell you if you're not handling all the possible errors that the kernel would return. And there was a lot of hype around memory safety. And I'd written in a memory safe language for years, JavaScript. And I knew with the security work I did, that most of the low-hanging security fruit is not actually, complex C buffer overflows. It's all JavaScript. Like it's JavaScript modules that get exploited and companies get hacked. Even HTML5, you can create a reverse proxy with the old HTML5 app cache. So for us, actually, we all saw Zig as a really safe language, and that was it was so much safer than C, and it was just really like C/Zig. And once we were all on board that C is the language, and obviously Zig is so much better, let's just replace C. It's pretty smooth.
Makes
and
sense.
It's credit to the Coil team because we also do a lot of Rust, but we wanted this to be a simple domain.
I see. When was that? Like in the timeline? I'm thinking of, was this before or after the nonprofit foundation, like the Zig nonprofit foundation?
It was before. So like I said, we were late to the party.
I see.
But it was before. So it was, I think the Zig Software Foundation was founded in July last year, and we were talking about this, I think just before, like in July, in June, somewhere there. It was concurrent, the same time.
Yeah, I can add there, Lars. So we were. Joran has this really cool habit of when he wants to have like a really detailed meeting, we do walking meetings. And so this was before, there was a lot of lockdowns and so on. So it must have been at least sort of early last year. And I'm not a systems level programmer. I don't know, my background is mostly Java. And so I must say, like, after having worked with Joran for a while and seen, the work that he and Don had done already, like with the Moduli project, he took us on one of these walks and he talked to us about Zig. And I was sort of thought, I trust you, like, you know what you're talking about. And so far, everything I've seen, has been outstanding. So if you believe in Zig as strongly, like he was really passionate about it, as you do, then then I think we should go for it. And I think the sell internally within Core was pretty easy after that. Like Joran shows a lot of passion for Zig, and that sort of comes through whenever he talks about it. So as he said, like we had a little bit of Rust development happening within Coil, but I don't think Rust was considered for more than 5 minutes once Joran got going. So I think it was a pretty easy call. And one of the biggest motivators was that we were sort of planning to build out TigerBeetle over about a year. So we had, Joran had laid out a really good roadmap for us to get to kind of production ready by next year. And he felt like the trajectory for Zig was going to just map exactly along with us, and that we would probably be ready to release, production level TigerBeetle, just as Zig was getting to sort of that level of maturity as well. So stars were aligned, and you had a very passionate Zig promoter in the team.
Nice.
And great leaders, like fantastic people at Coil. Awesome.
Awesome. I think that was a stroke of genius in a sense, because if it is before the non-profit foundation, I mean, I was sold on Zig also day one, but I'm also not in charge of a serious database project like yours. There's also that, but I think it makes sense, and the timelines seem to be aligned. That's awesome. So let me think of a couple more questions. Isaac, for you, I think you told us a while ago that you started working with the rest of the Tiger team, right, on TigerBeetle. So the question would be, I guess, how does it feel to have like probably you've taken the first Zig job?
Yeah, it's pretty surreal, but also just really awesome. I mean, I could not be happier to have this opportunity, to be honest. Because like at the start of the pandemic, I just kind of started learning Zig because it seemed like the best language for my compositor, and it really felt great. And so I was kind of like in the back of my head thinking like, should I just be getting better at C? Is that going to be easier to get a job with in the future? Is this really going to pay off? Like getting really good at Zig? And it seems to be paying off. So I'm going to be more thankful for that, and for also all the work you have done, and you and Andrew have done to make Zig what it is today, and just keep it on this upward trajectory.
Awesome. Oh man, I'm, by the way, I'm also lobbying this also because I occasionally stumble across comments on the internet that says, oh, Zig has 0 jobs. Well, no, Zig has how many of you are writing Zig? 3 of you?
All right. Yep.
Yeah. So at least 3 jobs out there. Amazing.
And we have another engineer in training. She's just joined the team. So Sarah's
Nice.
getting skilled up by the best.
That's awesome. That's very good to hear.
All 4 of us as well on the call, and that's another thing. Like Zig is so readable, so it's almost like TypeScript. Anyone who knows TypeScript, you can read Zig. So again, like Isaac said, it's just all credit to Andrew and to the whole Zig team, because it's just brilliant. Every design decision is just spot on, and so awesome. You guys are the ones making
that's
it
a really
all
good
happen.
point. Joran reminds me of something related to your first question, Loris, which when we were so there's a team within Coil building another project called Rafiki. It's all written in TypeScript, which is the main language we use within Coil, and TigerBeetle is a dependency of that project. And so obviously the Rafiki team, the TigerBeetle team have started working closely together. And I loved the first call we had together. One of the other engineers within Coil, who predominantly works in TypeScript, made exactly that comment. He said, wow, I've been looking through the code and I actually understand it. Like I've never read Zig in my life, and it was so easy to understand. So credit to the language, and as well as the work that guys have done. I think even for me as someone who's coming from a Java background, I find it pretty straightforward to understand like what's happening in that code and follow it.
Nice. Don, I have a question for you. So you make rockets, you write Zig code. Is there anything boring that you do? Like, do you occasionally stop and relax and do something generally boring, or is it always high-octane action for you?
No. On the weekends, I'm pretty much a couch potato. Like, just leave everything for the week and then just relax on the weekend.
Right.
I take really slow jogs. It takes me like 45 minutes to do a 5-kilometer loop. So yeah, it's not always high octane.
Okay. Good to know. Okay, let's see. Oh, there's a bunch of questions. Oh my God. Okay, let's go through the questions. There was one from before. I don't want to miss it. Okay, so the first question from LeafView. Will there be support for a non-static server list, and how would it work? I guess this was posted while you were showing the modular system, right? To elect the next leader, I'm guessing.
I take it so the question is a non-static server list. In other words, like LeafView, I think you mean. By the way, awesome work that you're doing. Your project is so awesome. I'm watching it on Twitter, and yeah, you're going to leave TigerBeetle's design in the dust. But yeah, the good news is we've got space for reconfiguration of the cluster, so you will be able to reconfigure. You can say, right, here's our list of 3 servers, and you will be able to add servers into the cluster, drop servers. So the ViewStamp replication protocol, especially the one that James Cowling did in 2012, the revision, that shows how to do reconfiguration. So you'll see our VR header has that in. It's called the epoch, but we haven't implemented that yet, and that's still going to be a few months out. For now, it's quite complex. So for now, we're happy with a static cluster set.
Next question from Andrew. Instead of going through all this trouble, why don't you just have eagles fly the money directly between bank accounts? That's a good question. Why don't you just use the eagles, right?
We'll see you in September for the Eagles.
There's a lot of
great question, Andrew. Adrian's probably the best person to answer that.
What, about the Eagles?
Yeah, yeah.
I think why go through all this trouble? I can answer that piece of the question. I think, like I alluded to in my section right at the beginning, I think there's a genuine problem here to be solved that no one really has ever recognized as a problem that they could solve a lot better than the way it's been done in the past. I don't know the deep history of a lot of different databases and why we have relational versus NoSQL versus key value stores and so on, why all these different forms of persistence exist. But somewhere along the line, someone realized they wanted to write a database with a more tightly scoped domain than just storing things in files or something like that. And so I think there's long overdue a data store that is specifically scoped to accounts and transfers, and it's a really nice tightly scoped domain that allows you to write something awesome like TigerBeetle. So it's highly performant, it's very safe, because of that tightly scoped domain. And I'm I love the fact that at Coil the culture is to build stuff like this in the open and make it open source. I really hope people take this and run with it. We're using it, as I said, internally in another open source project of ours. We're helping to make it a part of the Moduloop project. I hope anybody who is trying to solve this problem and has done it before through a weird combination of application code and generic databases has a look at TigerBeetle and gives it a run. I think there's a lot of scope to improve, the way financial systems are built, and I really hope TigerBeetle becomes an important part of that.
We also just figured, these TigerBeetles are so fast. Just tie those payments onto the beetles and send them off, because that's something with the name we didn't explain. But one of the big challenges in Moduloop was because, like, Moduloop is open, it's open source. Moduloop is going to change people's lives in Africa. If we can make it succeed, it's going to lift a whole lot of people above the critical poverty line by giving them access to payments for the very first time, instead of having kilometers, to just do a transaction. Moduloop will let them do banking on their phone. But the thing is that deploying Moduloop, if your database is not fast enough, if it can only do, a few hundred payments a second, and If the hardware costs thousands of dollars a month, that's a huge problem. So essentially, the equation is if we can have TigerBeetle, something tiny, just running on 3 office laptops. If that is enough to do 1 million a second, then it means that now someone can actually take Raspberry Pi servers much cheaper and get the throughput they need, because they're not going to need 1 million a second, but it's just an equation that lets you tune your cost, and that brings the operating cost down, which again and the whole idea is we want this Beetle to thrive in tough environments. So it's fast, but it's also small and cheap to run.
Right. So basically you're saying that in the end the hobbits should have been riding TigerBeetles instead of walking.
I think they do in the fourth Hobbit movie.
Okay, let's see. Next question from Helios. How are you handling these changes with each version? Are you using one specific version and sticking to it, or updating as it moves?
So until recently, we were tracking master branch, but since the 0.8.0 release, we've now decided to stick with 0.8.0 just to avoid the constant churn of keeping up with master branch, especially since we expect the 0.8.0 to 0.9.0 release cycle to be or even more churny than usual as the self-host compiler replaces the C++ compiler slowly. There's already been a lot of churn so far in this release cycle. And so our plan right now is to stick with 0.8.0 unless it doesn't make sense to do so anymore. And I'm currently thinking that we'll probably stick with 0.8.0 until 0.9.0 releases, and then we'll just do the upgrade in one fell swoop and make all the breaking changes at once.
Mm-hmm. Have you checked, out of curiosity, how many unused variables you guys have?
I've done some. I haven't found any bugs yet, which is kind of surprising, but I haven't checked all the code yet because there's a lot to go through, There's also other breaking changes that are separate from that, but I will definitely be trying to get some kind of automated check for that hooked up to our CI at some point. But yeah, very happy to see that work happening on master branch.
Yeah. Okay, let's see. More questions. Are there more questions? I think we got all the questions. Yeah, I think we got all the important questions. So,
all right.
Everyone, thank you very much for this presentation and for taking the time also to answer questions. That was awesome, by the way, really an awesome presentation. I think I'll leave you each a little bit of time if you want to say anything, and after that we can go on a break. So let's see, who decides the order? Joran, I elect you leader, you decide the order.
Okay, I nominated in the origin story order. So starting with you, Adrian.
Yeah, thanks very much, Loris, for having us. Apologies for my very poor effort at a Gandalf hat. I had a better one and it fell apart literally 5 minutes before the show. So that was the best I could do. But yeah, I really encourage people to join the follow-up call in September. I think it's going to be really exciting, and I've seen the build-up, a lot of what's happening in the background. So I think I'm looking forward to seeing the reaction to that call as well. And yeah, please, track TigerBeetle. As we said, it's an open source project that we hope really makes a difference in how financial services are built and delivered. And as Joran points out, one of the keys for us is building financial services applications that are easy for people to operate, but also cheap. And we hope that has a knock-on effect. Over to you, Don.
Cool. Thanks, Gandalf. Yeah, as Eddie said, thanks for having us. It's pretty cool doing a Zig SHOWTIME talk. Always been just watching it, so it's cool to see what it's like on the other side of it. And it's great team going on. Yeah, I just realized, did we say what the GitHub repo is? If not, it's it's that if you just go coilhq/TigerBeetle, and you'll find it there. Yeah, and then that's about it.
Yeah.
And Adrian was almost, Gandalf the Gold. That would be his Gandalf color. There's many Gandalfs, and Adrian is Gandalf the Gold with that hat. Well done, Adrian, and to everyone. And thank you, Larissa, for the hospitality. This has been since last year, when we decided on Zig as a language, it's Don and my dream goal, to be on Showtime. So it's such a privilege. Thank you. And to the whole Zig core team, keep on. It's phenomenal what you're all doing, and we're supporting you and the whole Zig community. Keep on surfing and keep looking for that dream wave and have the courage just to ride the quality wave. It's such fantastic quality. And see you all again in September.
Thank you. Wait, did I miss? Isaac still has to go, right? Yeah.
I'm not really sure I've got anything to say. I just pretty much kind of want to echo what everyone else has already said and just thank everybody for this opportunity. And thank you to Coil for making me the first Zig developer to be hired just for knowing Zig. And yeah, I'm very excited to see what the future holds for TigerBeetle and Zig.
Awesome.
See you guys in September.
Thank you very much. And so we can go to the break.